Hello student, in the last class we have discussed about similarity and distance, about how we can discuss or how we can find the similarity between two objects or two data sets or two samples using the various distance functions like equivalent distance. There might be also you can find Manhattan distance also, so like that. And another point to discuss about in that same range is like nearest neighbors for predictive modeling. We also can use the idea of nearest neighbors to do predictive modeling in different way. Take a minute to recall everything you know about predictive modeling from prior chapters. Predictive modeling is basically we can understand about how we can predict so whatever data we have from the past to predict the things in the future. To use similarity for predictive modeling, the basic procedure is to beautifully simple. Given a new example whose target variable we want to predict, we scan through all our training examples and choose several that are most similar to the uh, new example. Then we predict a new example target value based on the nearest neighbors target values. How do we do that? Last steps needs to define. For now, let's just say that we have some combining functions like voting or averaging operating on near neighbors known target values. The combining function will give us predictions. So here to predict new examples target value based on the nearest neighbors target value. How to do that? Last step means how to do the find nearest neighbor target value. Okay, in the figure 6.2 nearest neighbor classification, the point to be classified labeled with a question mark. That point is labeled with a question mark and would be classified as plus, and these plus things are that are going to be classified already not classified, and because the majority of its neighbor are positive, so here you can see this question mark point will be classified as plus because majority of these neighbor are plus. Only one is not plus, two is plus. Then only we can say that this object which is now question mark has been or going to be classified as plus. Here also the same thing is that we predict a new examples target value based on the nearest neighbors target value, but how to do that last step needs to be defined. For now, let's just say that with some combining functions like voting or averaging operating on neighbors known target values. These are known target values. So classification, since we have focused a great deal on classification task so far in the book or in our course, let's begin by seeing how neighbors can be used to classify new instance in a super simple setting. For figure 0.62 shows new examples, same example has been discussed here. Okay, adding just a little more complexity, consider a credit card marketing problem. The goal is to predict whether a new customer will respond to a credit card offer based on how other similar customers have responded. That data are shown in 6.1. So this is the data about the thing. So here the data of David is this one. Data of zone is this one, Rachel is this one, like that. Age is this, income is this, how many cards are there, and we don't know the response of David, and but we know the response of John, Rachel, Ruth, Jefferson or Nora. In this example, there are 5 existing customers we previously have contacted with a credit card offer. For each of them, we have their name, age, income, number of cards they already have, whether they responded to the offer. For a new person, David, we want to predict whether he will respond to offer or not. We try to find the distance function. Using distance function, what is the distance from the David? So here we try to use the Euclidean distance function. 35 minus 37 square, 35 minus 50 square, 3 minus 2 square. So in that way we try to find the distances. So here you can see which one are more closest to the David. So here you can see 15.74, 15.16 and 15. Those are more nearest to David. But among them only two are yes and only one is no. But these two are these two, Root and Jefferson, are more distant, so we might not consider these two one. So if this is a yes, 2 points are yes, then obviously we are going to choose this target as yes. That is the estimation, or that is the prediction, but it might not be true also. So let's see what we discussed. So a distance calculation using 61 of how for each instances from David, three customers are fairly similar to David with a distance of about 15. The other two customers, Ruth and Jefferson, are much further away. Therefore, David's three nearest neighbors are Rachel, John, and Nora. Their responses are no. And no, yes, yes, respectively. If we take a majority vote of these values, we predict yes. This touches upon some important issues with nearest neighbors. How many neighbors should we use? Should they have equal weights in combining function? We discuss it later in this chapter. So that is main questions here. So you try to give some focus on this question. How many neighbors should we use? And should they have equal weights in combining functions? Or we discuss like point is that which here we have chosen only in this example only 3, because these are the 3 values have been closest to the David. So that is how we are choosing. But why we don't go for 4? Or is there any specific reasons? So can we go for those specific reasons? Or is there any weight associated with it? Or is there any specific voting methods to be more to be neighborer? So that is the more important question in this nearest neighbor analysis. Probability estimation. We have made the point that it is usually important not just to classify new example but to estimate its probability, to assign a score to it, because a score gives more information that is just in rather than giving a yes no decision. Nearest neighbor classification can be used to do this fairly easily. Consider again the classification task of deciding whether David will be responder or not. His nearest neighbor, Rachel, John, or Nora, have classes of no, yes, yes respectively. Obviously we have seen it. If we score for the yes class, so that yes equal to 1 and no for 0, we can average this into a score of 2/3 for David. If we were do this in practice, we might want to use more than just 3 neighbors to compute the probability estimate. So you can follow the probability estimation technique that we have discussed previously to find the probability of David to happen, to find the probability of David saying yes, having the total number of events. And another point is regression. Once we can retrieve the nearest neighbors, we can use them for any predictive mining task by combining them in different ways. We just saw how to do classification by taking majority of vote of a target. We can do regression in a similar way. Assume we had same data set like this, table 6.1, but this time we want to predict David's income. We won't redo the distance calculation, but assume that David's 3 nearest neighbors were again Rachel, John, and Nora, and their respective incomes are 50, 30, 40. So then we can use this value to generate a prediction of David's income. We could use the average of about 42 or the median 40. So that is also a regression technique to determine or to predict the income of David by having the same knowledge of nearest neighbor from the previous examples of because we have already calculated the distances, so we are not going to calculate distances again in case of regression. If we have done it before, then we are going to only do the average or take the median of the income that that is having by Rachel, John, and Nora, that is 50, 35, 40. We will take the average, or we might take the median value to get the or to predict that income of David. So how many neighbors and how much influence? So that is a very big question. Um, in course of explaining how classification regression scoring may be done, we have used an example with only three neighbors. Several questions may be occurred to you. First, why three neighbors instead of just one or five or 100? Second, should we treat all neighbors the same? Though all are called nearest neighbors, some are nearer than others. Should not this influence how they are used? There is no simple answer to how many neighbors should be used. Odd numbers are convenient of breaking ties for majority vote classification with two-class problems. So there is no simple answer to how many neighbors should be used. Odd numbers are convenient. That is why we try to take odd numbers to break the tie. For majority vote classification with two-class problems, if we have two-class problems, then we can go for odd number of neighbors. Nearest neighbor algorithms are often referred to by shorthand KNN, where K refers to the number of neighbors used, such as 3NN. So we can choose this K value as odd. KNN algorithm you can find in the literature also. The K value will be 3, the 5 or 9 or something like that. In general, the greater K is more the estimates are smoothed but among neighbors. If you have understood everything so far, with a little thought you should realize that if we increase the K to maximum possible, the entire dataset would be used for prediction. Would be for every prediction. Elegantly, this simple predicts the average over the entire dataset. For any example, for a classification, this would predict the majority class in the entire dataset. For regression, the average all the targets values. For class probability estimation, the base probability. Even if we are confident about the number of neighbors, examples we should use, we may realize that neighbors have different similarity to the example we are trying to predict. Should not this influence how they are used? That is also a question. For classification, we started with a simple strategy, majority voting, retrieving an odd number of neighbors to break ties. However, this ignores an important piece of information: how close each neighbor is to the instance. For example, consider what would be happen if we use K 4 neighbors to classify David. We would retrieve the responses yes no, causing responses to be extremely evenly mixed, but the first three are very close to David while the fourth is much further away in the previous case. So intuitively these four instances should not contribute as much to the vote as the first three. To incorporate this concern, nearest neighbor methods often use weighted voting or similarity moderated voting such that its neighbor's contribution is scaled by its similarity. So here you can see, consider again the data in the table 6.1. So here again we are trying to put the thing, distance are written here, similarity weights are defined like this, and contribution is like this, and class are like this. So it depends greatly on a number of neighbors we choose. Let's redo the calculation, this time using all neighbors but scaling each by its similarity to David, using as the scaling weight the reciprocal of the square of the distance. Reciprocal of the square of the distance will be the scaling weight. Here are the neighbors ordered by their distance from the David. The contribution column is the amount that each neighbor contributes to the final calculation of target probability predictions. The contributions are proportional to the weights but adding up to 1. We see that distance greatly affect contribution. Rachel, John and Noah are most similar. Rachel, John and Noah are most similar to David and effectively determine our prediction of his response, while Jeffersons and Ruth are so far away that they contribute virtually nothing. Summing up the contributions for the positives and negative classes, the final probability estimates for David's are 0.65 yes and 0.35 for no, and that is why we will go for yes. This concept generalized to other sorts of prediction tasks. For example, regression and class probability estimation. Generally, we can think of procedure as weighted scoring. Weighted scoring has a nice consequences in that it reduces the importance of deciding how many neighbors to use, because the contribution of each neighbor is moderated by the distance. The influence of neighbors necessarily drops off the further they are from the distance. Consequently, when using weighted scoring, the exact value of k is much less critical than with majority voting for unweighted averaging. Some methods avoid committing to a k by retrieving a very large number of instances. For example, all instances k equal n depend upon distance weighting to moderate the influence. So you can understand as a whole, you can see if those values of Rachel, John and Noah are closer, then their similarity weight also be closer. Now that is taken by scaling weight or similarity weight is taken by 1 divided by square root of this. So that's it in this video about nearest neighbors. You can find more knowledge about this in literature also, in the other book also, and try to go through it. It is very helpful to understand the use of nearest neighbors in various problems, or in research problems, or in data science problems, or in business analytics problems. Try to go through it. If you have any problem, let me know. We'll try to resolve it over the Google Meet. That's it. Thank you.